I would like to welcome to all of you to Rio de Janeiro and to this meeting. This is the Iberoamerican Meeting in Geometry, Mechanics and Control. And as you probably know, this is the 4th edition of the meeting that was previously held in Salamanca in Spain, then in Bariloche, Argentina, which is my hometown, and then in Santiago de Compostela. I think I changed. Yeah. In Santiago de Compostela in Spain again. And now this is the first time that we have this meeting in Rio de Janeiro. And in this opportunity, as you also probably know, we are celebrating the 65th birthday of our friend Jair Koiller. So thank you to come down here to Brazil for this conference, and we are starting now with the scientific program of the conference.
Yeah, I don't have much to add to what Paulo just said. It's really a pleasure to have you all here. And I'll be making some announcements later on today about the social program and the scientific program. Let me just remind you right now that we have the Marsin lecture this afternoon, and there will be a reception right after that. And if you have any questions, you can let us know. Alejandro, me, Enrique, or Paula. And yeah, so I think that we're ready to just move on and start really with the first talk. I'm very happy to have A.Weinstein here giving the first lecture of the meeting. Alan was Jair's advisor a few years ago. He was also my advisor, some years after that. And he was also Milton's advisor somewhere in between me and Jair. So it's really a great pleasure to have him giving the first talk of the conference.
Thank you. So thank you. Thanks, Henrique. Thanks to everybody here for giving me a chance to come down here and see several of my old students, plus other Berkeley students. We're overly well represented here, I think. But there's always been a really close connection between Berkeley and IMPA ever since I was a graduate student, and Mauricio Peixoto was there visiting Smale and doing dynamical systems, and my fellow graduate student was Jaco, who you know very well here. And so I want to first wish happy birthday to the man in the hot seat here in the front row, and I guess we'll be hearing more about him, especially tomorrow. So I'll get right on to some of the geometry, mechanics, and maybe a little even tenuous relation to control. And here it's by mechanics, most of the geometric mechanics is I think classical mechanics, but there's also quantum mechanics. And what interests me the most is the interface between the two. And this talk is really inspired by problems in connection with that interface. So let me start with, I'll just leave this. This is, in case you haven't noticed it, this is the password for the Wi-Fi here. And if you've been here like I have in the last 2 years, it hasn't changed. So if your device is still, it may remember it. This is an N, right? Castorina. Okay, so the beginning of the connection between classical and quantum mechanics, I think it was made most explicit by Dirac quite some time ago, is to go between classical observables, which are functions on phase space, position, momentum, energy, various other Hamiltonians, and self-adjoint operators, or I times self-adjoint operators, which are the observables and the generators of symmetries and so on in quantum mechanics. And then on the level of the classical observables, we have Poisson brackets, and on the quantum side, we have commutator brackets, and this connection between the two is supposed to be as compatible as possible with the Poisson bracket structure and the commutator bracket structure. Now, these are both Lie algebras, and when you integrate them to groups, on the classical side, you get symplectic transformations, and on the quantum side, you get unitary operators. And for some certain technical reasons, but also for just conceptual reasons, it's often better to work on this level, this sort of global as opposed to infinitesimal level. So we want to go between classical canonical transformations and quantum unitary operators. And the model for this is if we take as our configuration space Rn, or just some, I'll just call it V. It could be any vector space. Maybe I'll call it, well, I better call it V because that's what I have in my notes. Then as the phase space, we take R2n, which we think of as V cross V star, although this splitting is not, I mean, it's not a canonical splitting. And to this, we associate on the quantum side something like L2 of Rn, if you want a Hilbert space, but actually, for certain purposes, it's well known that we should not just look at L2 functions, but distributions like constant functions, which represent a particle a stationary particle whose position, whose position is unknown. A delta function representing a particle concentrated at one point whose momentum is completely unknown. Now, the automorphisms of this are the 2n by 2n matrices, which leave the symplectic form, if I have coordinates q and p, the sum dqi wedge dpi invariant. And here we get the unitary operators. I'll call this H. So here we have the unitary operators on H. So immediately here you see one advantage of the going from the local to the global is that the infinitesimal symmetries are self-adjoint operators. They're often unbounded operators, but when you integrate them, you get one-parameter groups of, or more complicated groups of unitary operators, which are nice bounded operators. So ideally, one would want to associate to each symplectic transformation, every linear symmetry of R2n, a unitary operator on H. Now, at the level, going back to the infinitesimal level, the generators here are the QJs, which get implemented by the infinite. I'll write the symplectic, the self-adjoint operator here. It's just multiplication by QJ, and PJ goes to I times partial QJ, possibly, depending on how you're setting up the theory, possibly with Planck's constant in there as an extra factor. Then, of course, in order to get up to the symplectic group, you need to implement this for quadratic functions. And so, for example, QJ squared, well, that one's just the same thing. It's multiplication by QJ squared or multiplication by QJ squared. But if you take QJ, PJ, this gets quantized to MQJ. This gets quantized to I partial PJ. But this is also equal, on the classical side, this is equal to PJ, QJ. which means that you might actually think that there was this other term here. QJ, right. Partial QJ multiplication by QJ. And if you don't know which of these two to choose, you split the difference, take the average. And this actually works. If you do a similar thing, you can quantize all the quadratic functions, which are the Hamiltonians generating linear symplectic transformations, and you get self-adjoint operators which have exactly the same commutation relations as the Poisson bracket relations over here. And then you get the Lie algebra of this going to the Lie algebra of this, and you can try to integrate it. And everything works very nicely, except that when you take a vector, a Hamiltonian that generates going once around SP2n, for example, a harmonic oscillator going through one rotation, the operator you wind up here is not the identity, but minus the identity. So you have to take a double covering called the metaplectic group, and that has a nice representation called the metaplectic representation, and it includes a lot of interesting operators, the evolution of all kinds of systems of coupled harmonic oscillators, along with a free particle, and the Fourier transform is also in there. So that's a very well understood construction, and there are even some variants of it. For example, you can do this over a finite field. That's turned out to be very useful in understanding some problems in coding theory. And that was done by Shamgar Gurevich and Rani Hadani a few years ago. You can also try to extend it to the complex coefficients here. And then there are new problems that come about because some of the operators that you have to integrate are not self-adjoint anymore. There are things like that what you'd have to do to run the heat equation in negative time, and things just start blowing up immediately. So they're really it's a difficult question to understand what happens when you go to the complex numbers here, and that's been studied in some depth by Omori and his collaborators in Japan. And there's still some mysteries in that subject, which I don't want to go into today, because I really want to talk about a very different extension of the metaplectic representation, which involves operators that aren't unitary over here, and things that on the classical side that are relations rather than actual mappings. And these things come about when you want to relate, in particular, if we want to relate different systems, things that happen, for example, when you have a system and you reduce it to fewer degrees of freedom. So here the idea is that we have some symplectic manifold, I'll call it Q, I guess. And in here, you have some constraint submanifold, I'll call C, and we'll assume it's what are called, some people call first-class constraints. It's a coisotropic submanifold, which means that at each point, the symplectic orthogonal to the tangent space of C is a subset of that tangent space. I call that. So there's one of these things at each point of C. And because the symplectic form is closed, these form an integrable distribution. And so we can pass to the quotient C over. Remember, this is a manifold. This is a foliation. Now, if we're in the linear case, Q is a vector space, C is a subspace, then this is just the translates of a subspace, and we're really actually taking C modulo its orthogonal, and that's the case I'm going to be thinking about most of the time. And now we can go from Q to here by taking each point of Q that happens to lie on C and each point of Q that happens to lie on C and mapping it to its leaf for this foliation. So as far as the domain is concerned, it's a mapping, but it's not a mapping from here to here because it's only defined on C. Now, sometimes you want to go the other way, and so I can also go this way in the following way. I take any point in C perp, that means take one of these leaves, and map it to every point on that leaf. So now it's defined everywhere. It's defined on every leaf, but it's not single valued. It takes a lot of values. Well, both of these are relations, and they can be thought of as sitting inside the product of these spaces, where the bar here means I've changed the sign of the symplectic structure on Q. And it's not just any submanifold, or in the linear case, subspace of this. It's a Lagrangian subspace. It has exactly half the dimension of this space, and the symplectic form, or if you want to say the difference of these symplectic forms, is 0, which is another way of saying that this thing, in some sense, when you go from here to here or go from here to here, the symplectic structure is invariant in the only sense that it could be when you have something that's not a mapping. And this still fits into the context that I set up over here, because if you do have a transformation between two symplectic spaces, if you look at its graph in x cross y and you put a bar here to change the sign of the symplectic structure, then the graph is Lagrangian in this product too. So both these canonical transformations and these reduction or co-reduction operations all give examples of what have been for a long time called canonical relations. I think the term goes back to Hermander's paper in 1970 or 71 on Fourier integral operators. Nowadays, these things are coming up a lot in symplectic topology, and people have been calling them Lagrangian correspondences, which is also a reasonable name for them, but I tend to have stuck with canonical relations. On the quantum side, going from Q to C, like putting on some constraints, would correspond to an orthogonal projection operator from the Hilbert space to a subspace associated with the constraints. Or maybe not a subspace. If we go this way, this is more like embedding a subspace. So this is a different space that's sort of sitting outside. There's a big system. There's a smaller system with fewer degrees of freedom. This takes us from the big system to the smaller system. This way embeds the smaller system into the big one. And going back and forth is almost the identity, but not quite. This way is the identity. This way is some kind of like projection from Q into a smaller piece. Okay. So now the question is, can we quantize all these relations in the linear case to get something that's as good as the metaplectic representation? The answer is yes, but it's much more subtle, and that's what this. It's much more complicated, and that's what this talk is about. So first of all, let me just erase. So from now on, I'm just going to talk about the linear case, and make only a few remarks about the general case of manifolds. So if we have two symplectic vector spaces, x and y, then the Lagrangian submanifolds in here are called canonical relations, and I like to think of them as going from y to x. And sometimes I'll call it L of x comma y. Okay. And the reason for making them go in that direction is that if I compose this with something in here, I can describe the composition in terms of this space in a very nice way. I take, suppose I have an L1, a Lagrangian subspace in here, and an L2 in here. I can take their Cartesian product, which is a Lagrangian subspace of this Cartesian product. I can intersect it with x, this x, cross the diagonal of y, which is the graph of the identity, and hence a Lagrangian subspace here, and the product of this with z. This whole thing is coisotropic in this product of these four symplectic manifolds. And it's orthogonal, so I can take L, or I can take this intersection and then project it to x cross z bar. The kernel of that projection is 0 across the diagonal across 0, which is exactly the orthogonal, symplectic orthogonal of this space. And I get a Lagrangian subspace here, which I'll call L1 composed with L2, or sometimes I'll just write L1, L2. So this is the composition, and it turns out that this is always a Lagrangian subspace. Now, the nicest case, and we'll see soon why it's the nicest case, is that we can, is when this sum, this product here, is transversal to this subspace here, meaning that their sum is the whole space here. When that happens, it turns out that the kernel of this map is 0. So this intersection is just sort of one-to-one representing x cross z bar. If these are not transversal, then this space is bigger than it. This intersection is bigger than it is in the generic case. But then this map has a kernel which is exactly the right dimension, so that when we project down, we get something that's half the dimension here. So in this way, we get maps for any x, y, and z. I will go left to right on this one because I'm not going to compose these maps too much. So if I go from z to y and then from y to x, I can go from z to x. And this operation for all possible spaces is associative. And the diagonal is an identity map, and this gives us a category where the objects are the symplectic vector spaces and the morphisms or mappings are these canonical relations. So that's what one would like on the classical to be the thing on the classical side that we'd like to quantize. And notice if you let y equal x and you just look at the Lagrangians that are the graphs of canonical transformations, those would be closed under composition. It's exactly the same composition that I'm talking about here. And so anything we can do on this level would be kind of generalization of the metaplectic representation. Let me just say, just to be quite explicit, what I mean by this fancy diagram stuff here. I mean that if x, to figure out what pairs are in xz, I look at all pairs xy in the first thing, y prime z in the second one, and I require that y equal y prime. And when y equals y prime, I forget about it and I just look at the pair xz. Now, the generic case is when for any xz in the composition, there's only one thing that you can put in the middle. And sometimes I call that a monic composition. Now, one reason for writing it this way, in this more abstract form, is that you see already if we're dealing with manifolds and you intersect two manifolds, the intersection might not be a manifold again. Even if it is, when you map it down to this space here, you might not get a manifold as the image. So there are two kinds of problems that come up. And in a linear case, they're completely equivalent problems. So when one of them happens, the other one happens to the same extent. And they kind of balance out in a nice way. So that's the classical side. On the quantum side, we have say Hilbert spaces corresponding to x and y, and we want some kind of quantum operators this way, but certainly not. We don't expect unitary operators. These spaces might even have different sizes, so to speak. They're Hilbert spaces, so there could be unitary operators, even if they come from x and y's of different dimensions. But you don't really expect them to be unitary operators, for various reasons. So, but maybe just linear operators. One sees immediately that you have to have unbounded operators, and they can be even worse than some of the things than differential operators, which occur when you do the infinitesimal problem. For example, suppose, and this is a very important example, suppose z is just one point. If z is just one point, then Lagrangians of x and the point are just the same thing as Lagrangian subspaces of x, which I'll just write L of x, or submanifolds in the nonlinear case. And the Hilbert space of z of a point is just the complex numbers. This is a system with 0 degrees of freedom. So there's essentially there's only one wave function up to a phase. So you're looking at some kind of sorry, where did I? Let's call this op hx hy. So we're looking for some kind of operator from the complex numbers into h of x, which will be the quantum representation of a Lagrangian subspace or submanifold of x. And here you also see some issue of size. In some sense, the Lagrangian submanifold or subspace only gives you the direction of the vector here, but it doesn't choose the phase for you, or it doesn't even choose the amplitude. For those of you who know about geometric quantization, on this Lagrangian submanifold or subspace, you need some extra data, some kind of a measure, something like a measure on that object. Technically, it's a half density. Okay, so what do you get? What should you get? Well, it turns out that if we work in where our configuration space is R2, if you take a subspace of the form P is equal to AQ, then the thing that represents it in the quantum, on the quantum side is the function e to the I. And if there's an h bar in this story, you put it here in the denominator. You put a half here, and then you take the function aq squared. So when a is equal to 0, we just have the horizontal line, and this is just a constant function. Now, we are allowed to put a constant in here. a multiplicative amplitude. And what happens is that, what happens as this thing gets steeper and steeper as a goes to infinity, this thing oscillates faster and faster, although it's not oscillating quite so fast as at the identity, because this is q squared, and q is not growing as quickly. Q squared is not growing as quickly. If I look at the real part of it, this becomes a cosine, and what I get is something that looks like this with faster and faster oscillations. And if I multiply this by a smooth function and take the limit, I'll always get multiply and then integrate. The positive will cancel out the negative, and I'll get 0. However, if I multiply this by 1 over the square root of a, or the square root of the absolute value of a, if a is negative, then it turns out that this thing approaches a delta function. Delta based at 0. In other words, if I make this tall enough, then the fact that this piece is wider here now has a non-trivial effect and gives you a non-zero answer. When you multiply this by another function and integrate, you just get the function's value at 0 in the limit as a goes to infinity. So that says that we should quantize the vertical by a delta function, which isn't so surprising. I mean, in the physical story, a particle known to be at the origin has to have completely indeterminate momentum by the uncertainty principle, and the corresponding wave function, so-called wave function, is a delta function at the origin. Now, of course, that's not an L2, so we see that we can't really just take a Hilbert space. We have to replace it by some space of distributions. Okay, so that's an example of how we can quantize canonical relations. And in fact, it turns out you can quantize any linear canonical relation from between R2n and R2m by something that looks like a generalization of this and delta, things like these exponentials of quadratics combined with delta functions. And around 1980, Gilliman and Sternberg showed that this association, if you forget about the constants here, so we're doing a weaker thing where everything is just up, these operators just up to constants, so we don't have to worry about the densities on the Lagrangians. It's completely compatible with composition. Composition of relations goes over to composition of operators as long as these two things are transversal. And then they just say as long as those are transversal. And so what they say is we're quantizing a kind of what maybe some people call a partial category, in which you can only multiply certain pairs of morphisms, namely if they satisfy some compatibility property, like in this case transversality. So that was, 30 years ago or something like that, and I've been worrying ever since. What happens if they're not compatible? And the first thing you see is that if you try composing the operators that corresponded to those non-compatible canonical transformations, not only don't you get the right answer, you don't get any answer at all. A simple case is the following. Let's go from the following. We'll go from a point to R2 and back to a point. Here I'm going to use the vertical as a Lagrangian subspace of R2. And here I'm going to use the vertical also, but as a Lagrangian subspace of R2 with the symplectic structure changed. So I want to go from C to some kind of to distributions on R and back to C. And going from C to itself is just a number, linear transformation from C to itself is just a number. So what number should it be? Well, this operator we know takes the number 1 to the delta function. In fact, it takes any number r to r times the delta function. This operator here is essentially the dual operator, which takes a function and evaluates it at 0. So here we're going to take any function, and this is d prime of r, and take it to f of 0. And so if we do the two things here, we take a number to r, and what we get is r times the value of the delta function at 0. That's infinity. You could say it's infinity, but that doesn't exist as a number. So if we want to do this, then either we have to introduce infinite numbers, or we have to build a different structure. And if you just introduce infinite numbers, like if I just say this is this goes to r times infinity, then you depending on what your kind of infinity you're talking about, probably you completely lost track of this r here. So what I'm going to describe is a structure, actually structures on the classical and the quantum sides, so that we get a complete parallelism between the two kinds of structures, and for which we can actually do the compositions, and compositions will correspond. So we get what's called functorial quantization. Actually, I'm going to describe it in several ways, in increasing order of abstraction. And it's motivated in part by another property of this composition, which singles out the transversal pairs as the good ones. Namely, the Lagrangian subspaces of x cross y are a Grassmann manifold. They're sitting in the usual Grassmann manifold of all half-dimensional subspaces. It's a certain closed submanifold. This is a submanifold, and this is a manifold again. And so you would expect, since this is a nice geometric operation, that this should be a smooth function from this product manifold to this one. Well, it's not. And in fact, it's not even continuous. It's continuous only at those points in this product, in other words, those pairs for which this is a transversal intersection. You can stratify these Lagrangian Grassmannians or the pairs, you can stratify the pairs according to the dimension by which this fails to be transversal, meaning the dimension of the codimension of the sum of these spaces. And it turns out that it's smooth on each stratum, but it fails it jumps as you go from a stratum to a larger one. This was studied in some detail by someone named Christophe Sabot, by now 10 or more years ago, who gave a precise description of how this thing fails to be continuous. And I'll use his result in a little while. So one of the things we're going to do is we're going to modify the structure, even on the classical side, so as to restore continuity. And then we'll have to make a corresponding modification on the quantum side so that compositions, once again, get quantized by compositions. So most of this talk will be about the classical side, and the whole project is joint work with David Liebland, who's currently a postdoc at Berkeley, and part of it with Theo Johnson Freyd, who was a graduate student at Berkeley, is now a postdoc at Northwestern. So let me tell you the most concrete version of it first. I'm going to, instead of just Lagrangian subspaces of a vector space, I'm going to consider what I'll call indexed Lagrangian subspaces. This is the set of pairs L, and with some, I'm going to put an index such that k is a non-negative integer. And I'm going to identify the ordinary Lagrangian subspaces with the ones for which k equals 0. And k is going to represent a kind of degree of badness or singularity. It's a kind of degree of, maybe you can even think of it as a power of infinity. But it'll have different interpretations and different versions of the story. I have to tell you how to compose these things. L1, K1, composed with L2, K2. So now I'm thinking of L1 as a Lagrangian in X cross Y bar, and L2 as a Lagrangian in X cross Z bar. So now I'm going to go from here to here. What I'm going to get is, first of all, the usual composition. And the indices, first of all, are going to add, again, if you think of them as being like exponents, that makes sense. But now I'm going to add another term, E of L1 and L2. This is the excess, which is the dimension of the kernel of this map, which is also the codimension of this sum. It's the dimension of the set of y's and y primes equal, for which correspond to x and z equals 0. So it's the number of ways, or the dimension of the ways of getting from 0 to 0 via something in the intermediate space y. So it turns out you can actually check by hand, just using simple linear algebra, that this composition is associative. And the identity together with k equals 0 is an identity for this composition. So we have a category now where the objects are still symplectic vector spaces, but we've added this extra data, and we've modified the composition in such a way as to keep track of these bad compositions, of these excessive compositions. So you can check that by hand, and what I'm going to next thing I'm going to tell you is that this is now continuous, and then the rest of the talk will tell you some more abstract structures that lead you to predict this law here, which I didn't think of. You might have just guessed it, and then verified these things by hand. But you'll see that there's actually some abstract, some of them quite abstract pictures that lead you to these structures. But let me say something about the topology. I don't just take the topology of the disjoint unions of these things for different k, but I will draw a picture of it as a disjoint union, which I'll think of it as a kind of infinite skyscraper. Where each level is just a copy of the ordinary Lagrangian subspaces. So it's a product space of L with this discrete space, but it's not going to have the product topology. Namely, and this is inspired by the theorem of Sabot, I'm going to tell you what a neighborhood of a point is. So neighborhood of a point, well, of course, you want to be able to just wiggle a subspace here and keep the k the same. But we want to also be able to go downstairs. And as we go downstairs, we spread out a little bit. And so I have to tell you where you can go. So I'm going to give a relation, say L k less than, well, L prime K prime less than LK. And what I'm going to allow is I can go to all L prime K prime which are less than LK in a sense that I'm now going to tell you. And I'll let LK range over one of these neighborhoods, and then everything below that will constitute a neighborhood of the original LK. So what's below? What does this mean? Well, this picture suggests that the further down I go, the further away I can go. And in fact, what I'm going to require is that first K prime is less than or equal to K, so that K minus K prime is a non-negative integer. And I'm going to allow the distance from L prime to L be less than this distance of how far downstairs I've gone. What I have to tell you, though, is what this distance is, because it's not the usual geometric distance in the Grassmann manifold. It's equal to the codimension of L prime intersect L in L itself. So if you want to say it, if you choose it, the distance is choose a basis of L and take some of the vectors in L, take some of these vectors in L and move them outside to a set that remains a basis. And the number of vectors I have to move outside is this distance here. So when the distance is 0, I don't move anything. And that's why up here I can't move at all. But now I allow, as I said, I allow this LK to wiggle a little bit, and that lets the things downstairs wiggle a little bit, and I get this neighborhood here. And it turns out that with respect to this topology, this composition is continuous. Okay, so the next thing I want to tell you is one way, the way I originally found this composition law, and then, but it doesn't explain the topology. And then I'll explain another way that not only explains gives the composition law, it explains the topology, and it quantizes in a nice way. So the first way is based on some work in symplectic topology by Verheim and Woodward, Katrin Verheim and Chris Woodward, who are interested in the nonlinear case of manifolds. And their idea is the following. What we're going to do is we're going to look at, if I want to go from x to, or from y to x, I'm going to look at chains this will be x through some xn, which is equal to y, where each of these arrows represents one of these canonical relations. And first I'm going to take these as the morphisms from y to x, and the composition will be just put one after the other. So it's like composing paths. Now, this is associative. It doesn't have an identity yet, because if you put the constant path in front of something, you get a longer chain. It's not the same thing as constant path, if I put an identity map in here, it's not going to actually be the same thing when you're done. So we introduce a relation which says you can erase or add identity maps, but that's not enough. What I want to say is that if somewhere in this chain I have a pair for which the composition is good, for which the excess is 0, then I'm going to allow myself to erase the space in the middle. Or conversely, I can do the opposite of that. I can break any arrow into a nice composition of 2 arrows. And this gives a new category in which the morphisms between x and y are the equivalence classes of these chains of morphisms from y to something to something to something to x. And we have a composition, as I said, you just put one chain after the other. Now, it turns out that this is actually in one-to-one correspondence with L dot of x and y. For manifolds, it's much more, this is very interesting for manifolds, but there's no nice description of it. Let's look at the case where an x and y are a point. Then we go to these intermediate spaces. And let's just put one in. It turns out you can actually boil it down to having one intermediate space. So this corresponds to one Lagrangian, and this corresponds to another one. And composing them is essentially taking the intersection of them. Now, if you just look at the set theoretic composition, it just tells you, do they intersect or don't they? And for vector spaces, they always do because they contain 0. But if we want to keep track of excess, then we need to know exactly what the intersection is and not just whether it's there or not. And in vector spaces, the only thing that really tells you what the intersection is the dimension of the vector space. To a first approximation, in some sense, you can't tell two vector spaces apart if they have the same dimension. So that's what this thing comes from. And the composition law here then just becomes the composition law with concatenation here. So that's the first picture. But as I said, it doesn't, at least I wasn't able to figure out how to get the topology out of that, nor how to quantize it in a sensible way. And so the way to quantization comes from an idea that was presented in a lecture, I think in Jerusalem, by Ofer Gaber, not too long after that Gilliman-Sternberg paper was published. Gaber said, oh, I know how to do it so that you can make it perfect. And I got a letter from Shlomo Sternberg sometime in the early 80s, maybe 1982, which I promptly put in my file and forgot about until a couple of years ago when I was making space in my office to start sharing it with a roommate, office mate, which is what you have to do in Berkeley. At least we get to keep the offices, but you have to start sharing. And it was a great event for me because I found this letter, I read it, and it said, well, here's the idea, and Victor Gilliman and I are going to put this in the next paper. And I wrote to Shlomo, and I said, where's this paper? And he said, we never wrote it. So I had to work out the details, and I proposed this to David as a project. And not only did he work out the details, but he figured, this was all on the quantum side, he figured out how to do an analogous thing on the classical side. And it's all based on what's nowadays known as derived geometry. But they're ideas that go back to work of Sayre in algebraic geometry, I think in the 1950s, in which he explained how to do intersection theory correctly. And the model is, for example, if I have two curves intersecting like this, and I want to describe the intersection, if I just do it geometrically, it's a point. If I do it in another way, it's a point together with a little infinitesimal extension of the point. But on the other hand, if I move these things ever so slightly, there's no intersection anymore. And so we get a kind of discontinuity of the intersection, which is in some ways analogous to this discontinuity I talked about before. Now, what Sayre said was that the way we understand this is we consider the spaces of functions on these two curves, not just as rings by themselves, but as modules over the ring of functions on the big space. And then it turns out that taking the intersection is basically taking the tensor product of those modules. And what Sayre observed was that if you don't take just the tensor product, but you take what's called the derived tensor product, this is what shows up in algebraic topology, for example, if you have the homology of two manifolds and you want the homology of their product. To the first approximation, it's just the tensor product, but then there's something called the torsion product, which tells you that the way that's not quite correct. And there are also higher torsion products, and what Sayre said, you should take all those higher torsion products. So Gauber's idea, which really belongs to the theory of D-modules, which is kind of algebraic geometry for algebras of differential operators, is that if I have a Lagrangian subspace of some x, I should quantize it not by operators on h of x, but by modules over the operators on h of x. And when I take a composition, well, I first have a module over. This is just this is the opposite algebra where I change the sign of change the order of multiplication. A module over this is what's called a bimodule over x, hx, and hy. And if you take the tensor product of bimodules, you get another bimodule over the spaces on the outside. And this is the zeroth approximation, if you want, to what the quantization should consist of. It's the zeroth approximation because it works for the transversal case here, but it doesn't work for the non-transversal case. So you have to do a correction. Is that you don't take just the tensor product of these bimodules, but you take the derived tensor product, which means that you take these higher order so-called torsion products. And then you get something that gives you right on the nose the right answer. And it's stable with respect to perturbations, just in the sense that Sayre's original construction was. Okay, so that's the quantum side, and now in some sense that could be the end of the story, but it turns out that this quantum picture corresponds to a derived geometry picture on the classical side, and that's what I want to just say a couple of words to end this talk.
So
yeah.
Say it again, so you're taking modules and bimodules over the operators?
Over the operators. In fact, what you do is, if I have a symplectic vector space X, I can think, if I think of the operators, that would be polynomial differential operators. That's called the Weyl algebra of X. And so this is the algebra that you use. And so you take, in this case, you take the Weyl algebra of X, tensor the opposite Weyl algebra of Y, and then the Weyl algebra of Y tensor the if you have something in the middle, it becomes a left and a right. You're tensoring a left Y module with a right Y module, and that makes sense, even because these algebras are non-commutative. That's one of the key points here. Okay, so to end, what's the classical picture? Well, the classical picture is that we don't just consider a symplectic vector space, but we consider a complex of vector spaces. So it's a sequence of vector spaces together with a differential whose square is 0. And there's a good notion of a symplectic structure on such a complex, which I won't detail for you because I can tell you later if you want to know. Then there's a notion of a Lagrangian in this thing, which is another complex with a certain map into here that satisfies some condition that's analogous to the condition of being half the dimension and having the symplectic form pulled back to 0. this is all up to some kind of equivalence. There are notions of homotopy. And as soon as you have a differential, there are notions of chain homotopy. And these things enter the picture as well. Anyway, we get a nice category in which we now have, if I have two complexes, if I look at the derived Lagrangians in x cross y bar, then I can compose these if I go from y to x and from z to y. And this gives us a new category. And this is really what quantizes to the Gabor category over there. And it turns out also that if you keep track of the equivalences here, it turns out that these spaces, this looks like a very complicated space because there are these complexes, and you have to worry about the equivalences between complexes. It inherits a structure called a stack, in which you keep track of the ways in which things can be equivalent. And that's really the way you should think of these derived Lagrangian Grassmannians. When you have a stack, underlying it is something called a coarse moduli space. It's the space of equivalence classes. And it turns out that space inherits a topology from this stack picture. And that topology is exactly the topology of this so-called Sabot topology that I described here with these pyramids. So that's, in some sense, although it's very elaborate, not as elaborate as derived algebraic geometry, which takes hundreds of pages to set up the fundamentals for. This is somehow, I think, the right picture that explains this refined version of canonical relations in linear algebra. Finally, to end, I should say, well, how does this answer the question, what is delta times, what is the value of the delta function at 0? Well, I think in some sense here, the value, if I have a delta function at 0, it's represented by a certain Lagrangian subspace here. On the other hand, the complex number, the Lagrangian subspaces of a point are actually, this is the usual Lagrangian subspace of a point, which is the point itself, but there are these higher ones also. And I think the value of the delta function at 0 is this point here. It's the number 1, but on the one floor upstairs. Now, there should be some nice physical meaning, interpretation of this. It's related to multiplying the delta function by itself. You'd get the delta function again, but on the next floor up. I would love to know what that is, and I'll leave that to Jair to figure out. Thank you.